Imagine descending toward a supermassive black hole 4.3 million times heavier than our Sun, a place where gravity swallows light and bends time. For centuries, physics relied on Isaac Newton's view of gravity, an attractive force pulling objects together. In 1915, Albert Einstein provided a different framework with general relativity, demonstrating that space and time form a combined fabric that mass can physically warp. This grid represents a black hole as an extreme, localized, and infinitely deep warping of that space-time fabric. This distortion is bounded by the event horizon, a term coined in the 1950s, which acts as the absolute point of no return. To understand where our established laws of physics reach their limit, we can use mathematically accurate simulations to follow a plunge across that final boundary. The simulation begins at the outer reaches of a non-rotating supermassive black hole, matching the mass of the one at the center of the Milky Way. At a distance of 97 million miles, equal to the span between Earth and the Sun, we reach the accretion disk. This structure is composed of superheated, glowing gas that collects and spirals toward the center at extreme velocities. Moving inward to the 15.5 million mile mark, a second structure appears, the photon rings. This model shows how extreme gravity can trap light. Beams from the surrounding gas orbit the central mass one or more times before redirecting toward the viewer, creating thin, layered bands of light against the sky. While these photon rings represent a visual distortion of light, the most significant effects of this gravity involve the way mass alters the measurement of time itself. Extreme gravity causes time to dilate, which creates two distinct versions of the same event. To a distant, safe observer, an object falling toward the black hole appears to slow down, eventually seeming to freeze just outside the boundary. This diagram illustrates gravitational redshift. As the falling light struggles to climb out of the gravity well, it stretches into redder wavelengths before reaching the observer. Shifting focus to the falling node reveals the traveler's local perspective, where time passes normally. For the traveler, the outside universe is blue-shifted, light brightens, and the entire sky appears to shrink forward as they approach the velocity of light. At the 7.8 million mile mark, the traveler reaches the threshold of the event horizon. Cross left behind. Once inside the event horizon, no signal of any kind, including light and gravitational waves, can ever escape back to the outside world. Based on the black hole's mass, the traveler has roughly 12.8 seconds from crossing the horizon until they are destroyed. At 79,500 miles from the center, the tidal forces of gravity lead to a process called spaghettification. This vector graphic shows how gravity pulls harder on the front of an object than the back, stretching it into a thin string of atoms while simultaneously compressing it from the sides. Because matter is disassembled at the atomic level, no biological or mechanical structure survives to witness the center. In the final microseconds of the agonizing fall, the fragmented remains rush toward the singularity at the exact center. Here, the equations of general relativity reach a limit where our current understanding of the laws of physics no longer applies. The paradoxes found at this edge have led physicists to reevaluate the standard definition of event horizons. Stephen Hawking suggested that gravitational collapse might instead produce apparent horizons, leaving the possibility that light might not be trapped forever. Conflicts like the information paradox and the firewall paradox ensure that the interior of black holes remains a subject of active scientific debate. Black holes represent the boundary where our observations and our theories have yet to align, marking a frontier in our study of the cosmos. Uncovered space, the universe beyond what you know.